Hi there. I didn't write down the values that we calculated for this section the other day. So I'm just going to start here because I think that we made an error with the some of the values that we put in, because when I graphed it later on, I got the right graph for the gradient. So we were looking at the suspension wires, trying to fit a parabolic curve to these three sections. They told us that the minimum distance to the horizontal reference line, which is this dotted line along here, should be 8, and the maximum distance should be 9.5. So we're just making some assumptions that this shape here is exactly the same shaped parabola as this shape of B and this shape of C. So I think we did this bit correctly, where we fitted a quadratic function to section A of the suspension wires, and we expressed it in the form y equals ax squared plus b. They did want us to state A correct to 3 decimal places. However, I sort of left it as a fraction just for accuracy. So we started with the minimum value. So it had to be for section A, had to be 0.8. And the maximum value, which occurs 17 metres from the beginning of the bridge, is at 9.5. So we created two simultaneous equations, substituted into our first equation, and we found that A was equal to 3 on 578, which is about 0.005. So according to what they asked in the SAC, you should have kept everything at 0.005. I didn't do that, and I sort of kept it as 3 over 578. Okay, so we did that bit, I think, correctly, and then it was when we did the translations, I think, that we might have stuffed up. I'm not sure. Transformation, if we think about it from this minimum value, so to get from this minimum value here and to translate the graph over here to this minimum here, we need to move the graph 34 places to the right, 34 units to the right. So our transformation matrix should have just looked like this. I can't remember if we had 34. I feel like we had the wrong value there, but it should have been 34. And then to write the function that models section B is just to put 34 in 34 as a translation into our equation that we had already for A. And again, you should have had 0.005 there. Oops. Section C can also be produced by the transformation. And again, looking at that minimum, we see that the minimum should have been moved 68 units along to so that it's in this position here. And when we put the three functions together to make the hybrid, we should have had the x squared, the x minus 34 squared, and the x minus 68 squared. And our domain values for each portion of the hybrid functions should have been from 0 to 17, 17 to 51, 51 to 68. So I think that's roughly where we were. And then we found the gradient function. So if you were to find the gradients of each section of our initial hybrid function, so just multiplying everything by 2, which brings us to 3 on 289 of x. For the last two portions, you should have used the chain rule so that you arrive at these two functions here. Oh, go away. 3 on 289x minus 34 and 3 on 289x minus 68. And I've just left it like that. You could expand those brackets if you liked. So I did sketch them, and I sketched them on the CAS, which is what we were trying to do yesterday. That allowed me to find all of the important features. So on CAS, We input not our derivative function. I think we did input our original hybrid function in our CAS. So if you've forgotten how to do that, to input the hybrid function, you go to this little button here, and there's a hybrid function with 3 parts to it. Oops, escape. So once we've input our hybrid function and we want to find the derivative of that function, we can do that simply menu, calculus, derivative, and that will bring up ddx. And then we can just input our f1 of x. I actually might do it so you can see. So again, remember that I call each function F4, F5, because that allows me just to graph it immediately. So F4, and you can see it's come up in bold because I've actually already defined it here. So it's just warning me that I already have a graph stored as F4. So F4 of X, we're going to define it. So it's control and then menu for calculus and derivative. We are finding the derivative with respect to X. We want the derivative of our hybrid function f1 of x. So we need to put f1 of x in here. And we've defined it. So that's exactly what I already done. So when I graphed f4 of x, I'm trying to think which one it is here. Oops, sorry, I've got a couple of graphs going on here. No, that's not it at all. It's this one. There it is. There's our derivative of f1 of x, which looks correct. So we've got a derivative which is constantly in the positive, and then we've got a derivative that begins negative, goes to 0, and then ends up in the positive, and then another derivative that is always negative, which makes sense if we look back at our, where is it? Diagram here. We can see that we've got a graph that begins at 0 gradient, and then has positive gradient. And then we should have a negative gradient reaching 0, and then a positive gradient, and then we should have a negative gradient until 0. And of course, the derivative of a quadratic is a linear function. So that's looking much better than it was the other day. So we can get the key features from CAS so that we can form our graph. So to get these features, that's just a maximum. So it would just be finding menu, analyze graph, maximum, lower bound, upper bound. And it does give a decimal here. 0.176 is that maximum value. On the graph that I drew here, whoops, where is it? There it is. I had a fraction, and that's because I just substituted the value 17 straight into the hybrid function here. And so 3 times 17 divided by 289 is just 3 on 17. And then it makes sure that you've got all of those endpoints as open endpoints, because the derivative does not actually exist at the cusps. So the cusps being those the points where the wires meet, and of course it doesn't exist at the end either. The next thing is that you're asked to find the angle that the wires make with each other where they meet. So if you imagine the 2 wires coming up like this, we want to find this angle that's in here. So I just sort of thought about, okay, well, I need to know the gradient at this point right here, and I need to know the gradient at this point right here, and I just extended those tangents up here, and then this angle theta is the same as this angle theta here, because vertically opposite angles are equal. So if we want to find that we know the gradient of the line here, we can find the angle that makes with the x-axis. Remember, we're finding the angle that it makes with the positive direction of the x-axis. So we actually know the gradient at the cusp, at that point where the wires meet, because that's right here, and the gradient there is 3 on 17. So finding the inverse tan or arctan of 3 on 17, we find that that is approximately 10. In fact, it's like 10.00, something like that. So I'm going to leave that approximation as 10 degrees. So if this angle here is 10 degrees, by symmetry, this angle here also has to be 10 degrees. So we can say if this is 10 degrees, this is 10 degrees, then the angle between them is 180 minus 20, which is 160 degrees, which kind of looks right with the diagram. So far, so good. Their diagram actually looks pretty good. See it there. 160 degrees. I can believe that angle there is 160. Okay, so the next part was a bit weird. Oh no, this part was good. It was the next part. It was the part after that was weird. So we want to find the vertical distance between the bridge and the suspension wires. So the distance between this suspension wire and the bridge, and they've asked us to do that at 3 key points. So they want to find the vertical distance between the bridge and the point where the set of wires meet. So that's the distance from here to the bridge. They also want to find the minimum vertical distance between the bridge and the wires and the maximum vertical distance between the bridge and the wires. So we want to find the distance. So to find the first part, we know that this is 17 meters. 17 meters from here to here. So we want to find the distance where x is equal to 17. The minimum vertical distance, now visually I just looked at that and said, okay, well the minimum vertical distance has to be at the highest point of the bridge and then the lowest point of the wires. So the minimum distance occurs at 34 meters. The maximum vertical distance, and I wasn't quite sure, so it does actually occur, the maximum vertical distance is actually right here at the ends of the bridge, or on this end of the bridge, it's 8 meters, but that was an assumption and I was right. So what I actually did was I sketched an equation for the distance, which was the hybrid function that we had for the wires minus the function that we already defined for the parabola early on in the SAC. So I think it kind of was way back here somewhere. So there's my hybrid function that I used, was the w of x. Way back. Well, before that, it was wow, it was right back at the beginning. This one. So right back on page 1 of the SAC, we worked out what the parabolic equation for the bridge could be. Now the easiest way to do it is to do that on CAS, sorry. So let's have a look. So on CAS, I defined the hybrid function. Then I also defined the, that must be it, the parabolic bridge function that we worked out from section 1. And then what I did was, so there's my, there's the wires and there's the bridge. So F1, the wires, F2 is the bridge. And then to find the distance, I just did F1 minus F2. So the distance between the wires minus the bridge. And I get this funky looking curve here. But I can see here that the minimum distance occurs at 34. The maximum distance occurs at 0 and at 68. And then I can also see or find, I'll get rid of that so you can see what I did. So I can also find what that distance is where the wires meet. So to find that, I just analysed graph, and it is also a maximum between here and here. It is a maximum. Oops, why have I got a funky value there? That's wrong. Try again. Maximum, I must have pressed minimum. Maximum between here and here, and that's it. It's better. And I get 7 1/4 for that distance here, or 7.25 meters. So you could do that by substituting into the formulas, and if you put 17 into our hybrid function for the y's, you'd get 9.5. 17 into our parabola function that we had at the beginning, you get 2.25, and 9.5 minus 2.25 is 2.75, which is the value that we got. And similarly for the minimum and the maximum distance, you could do those by substitution as well. But that would have been an assumption. So that's why I graphed it, to make sure that they truly were the minimum and maximum values. I didn't really like what they did with the last page. It's kind of a bit of an odd added section. So it asks us to use an alternate model for section A for the suspension wires, and I think that this is y equals minus cosine x on n plus n. So it's a bit faint on mine, but it makes sense for that to be negative. Also, they didn't tell us whether this was radian or degree. I'm assuming it is in degrees because the rest of the SAC was in degrees. So n is a natural number, which means it's one of the whole numbers, 1, 2, 3, 4, 5, etc. The best way to do this is to use a slider on CAS. So I'll show you how to do that in case you don't know. We do know that the minimum value should be 8 and the maximum value should be 9.5, which occurs at 17 meters along the bridge still. So they should be on the curve. So just substituting in the first point here, 0, 8. Cosine of 0 is 1. So we have 8 minus 1, which means that n should be 9. And I'm going to use that as a starter value. I'm not going to worry about this point yet. I'm going to use this as a starter value and see if I can get close to this point on my CAS. So we have negative, cosine of x divided by n plus n, and we are on the domain 0 to 17. When we press enter here, we get this thing that says, do you want to create a slider for n? And we do. So say OK. We do need to change the settings for our slider. So you click on the slider, you go to settings. We want our variable to be n. Our value is happy to start at 1, but we want our minimum values. This is the values that we are going to be using are natural numbers. We may as well start at 1. We know we need to go to at least 9. How about we go to all the way to 12? And we'll make our step size, as they are natural numbers, 1. While we're at it, we are going to change our window settings. We are only interested in x values from 0 to say 18. Y values from 0, we need to go at least to 9.5, so let's go to about 10. Okay, so looking at the graph that we've got at the moment, that looks nothing like section A of our wire curves. The wire curve looked kind of like half a parabola. That looks wrong. So if we change the steps on our slider, as we go up, that graph begins to look more and more like the graph that we require. So we'll go all the way to 9, and we see that it looks quite accurate. It does start here at 8, and we're not quite sure what this value it goes up to is. So let's have a look. We will get those values. Menu, analyze graph. Might as well get this value here. Actually, that's not going to work. It is 8. You can count up on the actually no, we don't know what the scale is there, but it is 8 there. So if we know that because we worked it out before. It's going to work out the maximum value instead. So we know this value is 8 because we worked it out before. This maximum value here at 17 is 9.3, which is close to the required maximum of 9.5. Let's see what happens to that value as we slide to 8. So if we made n equal 8, that value is further from 9.5. Sorry about Cassie, she needs feeding, so she's just going to cry. I'm sorry. If we go to 10, we see that that value then has exceeded 9.5. So really, we can see that the best value to choose for the model is n equals 9. So just writing that in there. So the best value for n is when n equals 9, and we have this situation that we have 0.8 here and 17 9.31. So it's as close as we can get. They do ask us to explain which of the two equations, the quadratic or the cosine function, better model section A. I'm not really sure what they were looking for here. I'm going to guess that the hybrid quadratic function, because meta models section A as the required maximum and minimum values on the quadratic function could be reached. We couldn't quite get there with the cosine model. The truth is that a hanging wire will in fact take the shape of something called a catenary. A catenary is when we have a wire hanging between 2 points or a rope hanging between 2 points, and it's how that particular hanging structure hangs under gravity. So neither of those models are going to be perfect because they don't model a catenary. You would need to know a little bit more about hyperbolic, cosine, and sine functions in order to model that graph correctly. This next bit doesn't make much sense either. They ask you to write a hybrid function for section B. I think they mean a hybrid functions for section A, B, and C. And we're just using the cosine rule that we established in part A, which was to use n equals 9. And we're going to shift it similarly as we did before, so that part B of the wire is part A of the wire translated 34 units to the right, and part C is part A of the wire translated 68 units to the right. So I think that's as best as I can do for that last part, because I'm not entirely sure what they were getting at here. Anyway, good luck, and let me know if you need more explanation for any of those parts.